Hello, class. Welcome back. This is lecture 5. Today we are moving on to talking about series, which are different from sequences. They sound the same and people get mixed up. So first, let's remember sequences before we move on, so we can compare them directly. So last time we studied sequences. So remember, those are just lists of numbers that go on forever. So they look like this. If you start out counting at 1, you could also start counting at 0, or something else. And then what did we do? We want to know whether they converge or diverge. So what do these things mean? This means that the list approaches or goes toward a number and diverges means it does not do that. Does not do this. So just lists of numbers that usually have some sort of pattern that they follow based on the fact that you can write the nth term using some kind of formula. And then so when you figure out this convergence or divergence business, you basically always deal with this formula if it's given to you, or you figure it out and then deal with it. And you take some sort of limit maybe, or you can use the squeeze theorem, or check if it's increasing and decreasing and bounded. That's the stuff we've been doing. Okay, so sequences, the word sequence sounds very much like the word series. I guess that's why people get them mixed up a lot. Next, we study series. And you can think of them as coming from sequences, but they're not the same thing. So all they are is what you get when you add up all of the terms. So here you're just listing them out, and that's a sequence. A series comes from adding them up. Okay, so they are the result of adding the terms of a sequence. Okay, so we need to learn some new notation to deal with this because we have to do so much adding. So here's the notation that'll help us with that. So this is sum. It's called a capital sigma. So it means add. Add what? It means add the terms A, I'll use a different subscript, K, where over here, you write what K starts at. So you put, if I want to start counting at 1, I put K equals 1. And then here, you put what K ends at. So if I want to end adding at K equals 7, then I would put a 7 there, for example. So then what does this really mean? It just means add. It means add A, and then you replace the K with the first number, 1, and then you add, and then you go up in the index. So K started at 1, so the next number is 2. So then you add up A2, and then you go up again, and you keep adding until you get to the 7th A7 until K becomes 7. K is what's changing. So this will be A4, A5, A6, A7. So 7 is the last one, and that's why it's the end. 1 is the first one, and that's why it's the beginning. So it's very shorthand notation for adding lots of things together that obey a pattern. So it'll come in very handy here. Okay. So just another example is you could change the notation around a lot. So basically whatever letter you put in here, so often people use I, is what needs to be here. So now if I wrote AI instead of AK, if I just change the name of the index to I, it still works exactly the same. So this would still be replace I with 1, replace I with 2, replace I with 3, and add them up. And you can change the letter, and you can also change the starting spot. So you can do something weird like start at -2 and go to 1. And this doesn't have to always be A, maybe it's B, but the index needs to be matching because that's what's changing. So this is just saying that you just change N and add. And then this is saying the same thing, but with I, change I and then add. Okay, so this one would be weird. It would be B -2 plus B -1 plus B 0 plus B1. You start at -2 and you go to 1, and you're always just counting whole numbers. So you're not going to worry about any sort of fractions or anything. But yeah, that's all. Okay, so that's the notation. So now if you have a sequence, specifically, so here we don't have actual sequences. These are just general names of sequences, these things. But if I have an actual sequence like, I don't know, how about 1 over n, then I can be more specific about something like this. So again, I don't have to use the same letter. It can get a bit confusing. Those don't have to be the same because what matters is that K is just ranging from 1 to 4. And this N just represents the nth term in the sequence. So you can still use it the same way. So here I change K to 1. I add, I change K to 2, I add, I change K to 3, I add, I change K to 4. And now that I know what AN actually is, I can use this. So what's A1 actually? Well, if I wrote out the list, A1 would be 1, A2 would be 1 over 2, A3 would be 1 over 3, and A4 would be 1 over 4 in the sequence, and so on like that. And so those are just these things here. Of course, I don't have to go write out the list. I could just jump to this step and I could just say, I know that this is a 1. I know that this is a 1 over 2, 1 over 3, 1 over 4. So the difference here is we're adding. Again, it's all about adding for series. And here we're just listing. That's why it's just a sequence. Okay, so that's the sequence over there, which is just a list. The series, this is not technically the series yet. This is still leading up to the series, but the series has to do with adding. Okay. You could also just skip ahead and not give a sequence. You could just write things like this. And I'm going to keep changing the index around just to mess with you, I guess, but it's good practice to see that it doesn't have to always be the same. So you could have something like n squared over 2 or something. So what does this mean? This means plug in 1, add, plug in 2, add, plug in 3, and add. That's what that means. And then you can actually add it if you want. So notice I don't have to write out the fact that this is going to be like A1 through A3, but it really is again. But I can just directly plug in the numbers 1 through 3 into the little formula here and write it out very quickly. So here's another one, different letter, I equals 2 to 4, I over I factorial, super weird. So what would this be? This would be 2 over 2 factorial, because I'm starting at 2, plus 3 over 3 factorial, because 3 is the next number, and then 4 over 4 factorial, because 4 is the last number. So you could have that, and really this is coming from, if you want to think about it like that, it's coming from the sequence where I just take these guys and I list them here. But whenever we use sequences, we typically like the letter N. So maybe I'll change it back to that. Okay. All right. So again, sequence versus adding different things. So a series, what it really is an infinite sum. So this is really what we're talking about. Above is just finite sums. We're just stopping at some number like 4 or something like that. But we don't have to stop. So given a sequence, because the sequence doesn't stop, it has infinitely many terms. As you go down and down and down, we want to define an infinite series, or just series if you want. You don't have to say infinite series because the infinite is implied. As well, the notation is going to look something like this. Instead of putting a specific number at the end here, if I want to add up infinitely many terms, and I don't want it to stop at a number, then what can I write? I can write infinity. And what that will mean is that I'm going to add A1 plus A2 plus A3 and so on, and I'm not going to stop. I'm going to add up all infinitely many terms of the sequence. But there are some issues we have to deal with. But this is how things are going to look. So we can't just add infinitely many things. We don't really know how to do that. I can add up 10 things. I can add up 100 things. It'll just take a while. But you never learn in kindergarten how to add up infinitely many things. They don't teach you that for some reason. So we got to figure that out here. So whenever you're dealing with the infinite, you typically have to invoke the power of limits. So that's what we're going to do here. So we must resort to using limits. And so let's think about that. Okay, so let's try to figure out what the heck this would be. So I'm going to start counting at 0, and I'm going to go to infinity, and I'm going to add up the terms of the sequence 1 over 2n, 2 to the n. So just notationally, this is supposed to look like this. 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 cubed plus so on forever. That's what it's supposed to look like. But you might be thinking like, okay, well, this is all stupid, because if I add up infinitely many numbers, which is what I'm doing, so I'm really doing like 1 plus a half plus a fourth plus an eighth and so on, then it should just be infinity because I'm adding up infinitely many numbers, right? That's what people typically think should happen, but it turns out to be much more interesting than that. So this will not be an infinite number. And how can we figure this out? So first, big step to get to infinity. First, start by adding finitely many terms. So don't worry about big, scary infinity yet. Let's just think about keeping it simple. So we're going to do one term. So one term is kind of weird. That would just mean n equals 0 to 0 because you don't add any extra terms. So that would just be 1 over 2 to the 0 without anything else added, and that would just be 1. Two terms would be from 0 to 1, and so that would be 1 over 2 to the 0 plus 1 over 2 to the 1, which would be 1 plus a half, which I'm going to simplify as 3/2. So we're going to do this a couple times because we want to see a pattern. And I'm going to sort of skip ahead. So this one is going to turn out to be 7/4 once you get a common denominator, but it's really a half. Sorry, it's 1 plus a half plus a fourth. So notice that each one contains the previous one. So maybe to establish the pattern, I'll write one more. But so it's going to be 1 over 2 to the 0 plus 1 over 2 to the 1 plus 2 squared is 1 plus a half plus a fourth. So notice that's there within it. And then again, as I said, that adds up to 7/4. Okay, so I guess I want to do 2 more to try to see the pattern. Oops, so this one will be 15/8 once you write it all out like this, like I did earlier. And the next one will be will be 31/16. Okay. So then the idea is, all right, fine, maybe I can't add this, but I can add this, and then I could add this, and then I can add this, which is what we've been doing down here. And I can see if those numbers follow a pattern. So here are the numbers: 1, 3/2, 7/4, 15/8, 31/16. So do these, I'm going to call them what they are. They're called partial sums because they're not the infinite sums. Do these partial sums follow a pattern? Meaning, are they themselves another nice sequence? So what we're going to do is create a new sequence. So using these partial sums. So S1 is really just the first number, which I guess was A0 because we started counting at 0 in this problem. And so that was just 1. S2 would have been A0 plus A1. That's what this was, A0 plus A1, if I originally named the sequence 1 over 2 to the n, starting at 0 for n. So capital S stands for partial sum of however many terms. So S2 stands for the partial sum of the first 2 terms. So that was 3/2. S3 is the partial sum of the first 3 terms, which was 7/4. S4 was the partial sum of the first 4 terms, which was, what was that, 15/8. And S5 was the partial sum of the first 5 terms, which was 31/16. So we want to know is, if I think of this as a sequence, so I'm going to call it SK instead of N, because I don't want my indices to be the same for my two different sequences, because I might need them to be different later. So basically, I'm looking at this pattern here: 1, 3/2, 7/4, 15/8, 31/16. And I'm asking, is there a nice formula for SK? Normally I would call this like AN and try to find AN, but now we're finding a formula for SK. So this one's a bit hard to see, but what it really is on the top, or well, the bottom is not so bad. These are just powers of 2, 2, 4, 8, 16. So these are just powers of 2. If I start counting at 0, well, actually, no, I guess I start counting at 1, because K stands for how many things I added up. And so here I added up 1, so I started at 1, added up 2 things, so I wrote 2. So starting from 1, if I think about this as 1 over 1, then this is really 2 to the 0. So this is going to be K minus 1 in order for that to match. And then on the top, these are just the same things, powers of 2, but minus 1, right? 3 is 4 minus 1, 7 is 8 minus 1, 15 is 16 minus 1. But it's always the next power of 2. So it's 2 to the K. And then you subtract 1 once you do the power, right? So that's the kth term, which, since I called these things partial sums, I'm going to call the kth partial sum. So essentially what we've done is we've said that, okay, I don't know how to add this up because I can't add up infinitely many, but I can add up K terms anytime I want. So how can I notate that? That just means instead of putting an infinity up there, put a K up there, because that's what I'm adding up to. Because that just means A0 plus A1 plus A2 plus ... plus, and then in between, we don't know how far to go, so we put that ... but we don't just leave the ... as if it were infinitely many terms. We go to the AK, and that's the last one. So that's what this is, and this is really SK, which we just figured out, which is this thing up here. It's a very long argument, so try to stick with it. So now, how can I add up infinitely many terms if I know how to add up finitely many terms up to any number K? So I could put whatever I want here. I could put 1,000, I could put 10,000, and I could still do it because I have that. This is really just SK, and I have a formula for that, which was 2 to the K minus 1 over 2 to the K minus 1. Well, if I want to add up to infinity, what would a good idea be? Why don't we just take the limit as K goes to infinity? So then that should be as if I'm adding up infinitely many terms, because I'm making this go to infinity. I'm making the kth term not really be there anymore because it just goes on and on forever. So that's what we're going to do. And that should be the finite sum. The infinite sum, I mean, sorry. So the idea is that this limit of the partial sums is going to be the infinite sum. Okay, and that's how we'll actually define the infinite sum. All right, so I know how to do this limit in this specific example. So let's do it. So it's really this limit as k goes to infinity of the partial sums, which we have a formula for. And let's just put that in there. Oops, sorry, that was a typo. This should be a -1 down there. This should be 2 to the k minus 1. So how do I take this limit? Well, there's various tricks you can use, but let's just do it this way. We'll just use some algebra. So this is really 2 to the k over 2 to the k minus 1 minus 1 over 2 to the k minus 1. And then those powers of 2, they're both base 2, so I can just subtract the powers, and this ends up as a 2, because I have one more power of 2 on the top than I do on the bottom. And now over here, this guy goes to 0 because the bottom is 2 to the k minus 1. So as k gets very big, this becomes a very tiny fraction going to 0. So this just becomes 2 minus 0 is 2. So we conclude that the initial infinite sum we were looking for should just be 2. Or in other words, 1 plus a half plus a fourth plus an eighth plus, and then so on in the same pattern, should just end up being 2. Okay, so then the cool part is we added infinitely many numbers. And we get a finite answer. Okay, so I just want to summarize how this works in general, because there's a lot of steps. And as you can see, even one example can take quite a while. So here's the summary. So given a sequence, so it could start at 1 or 0, it doesn't matter. I started the last one at 0, but you can start this one at 1 if you want. Given a sequence, it's kth partial sum. Okay, so you just have a list of numbers. They're just a boring old list, but then you add them together, you get its kth partial sum. That's called SK. And it just means add up the first k terms. So it's really just the sum of the first k terms. So this can get a little bit annoying. If this guy didn't start at 1, it would be a bit trickier. So just on the side here, like if I started at something else, it would be sort of tricky. So if I started at 0, well then SK, the first k terms are actually A0, A1, all the way up to k minus 1. Otherwise, you get more than k terms. So we sort of didn't deal with that, but I think that happened up here too. So this is actually a little bit off because Here it was okay because S1 was adding up one term, S2 is adding up two terms. So really SK should have been adding up like K minus one terms. So you get little annoyances like that. So it's easier just if you just stick with starting counting at one here, like this, it'll make things simpler if you can. Okay, we'll take it as it happens during examples. Okay, so in any case, this is the kth partial sum. So this creates another sequence of the partial sums. So SK, we think of it as a sequence. So S1 is just adding up one term together. S2 is adding up the first two. S3 is adding up the first three, and so on like that. So again, this guy would just be A1. This one would just be A1 plus A2. This one would be A1 plus A2 plus A3, so on like that. So this sequence, we know how to deal with sequences. So what we really care about is if this sequence converges, then that is what it means to be able to add up infinitely many things. So this sequence is just a bunch of things added together that get bigger and bigger. And if that sequence converges, that's what we call the infinite sum. So if this sequence that we created converges to a limit L, i.e. that's what we just did at the very end there, we took the limit as k goes to infinity. If that happens to be a number like it was 2 in the previous problem, then we define the series or infinite series to equal this limit. So the infinite sum is whatever that limit is. In the last problem, that was 2. So if that sequence diverges, then the series diverges, is what we say. Okay, so these are a bit tricky. They're very, very tricky. And so later in the class, what we learn is like we don't really deal with these that much by hand because they are so tricky. So here's an example. So here is a series. So if I just want to sort of see how it looks at the beginning, I can just plug in some numbers. So I plug in 1, I add, I plug in 2. I guess I can do it like that. I plug in 3, plug in 4, and so on forever. So that's how the infinite series sort of looks. And we want to know if it does this converge or not. Just like for sequences, we ask sort of the same question, but we figure out the question in a completely different way. So for the sequence, if I was just looking at the sequence, I would be looking at this thing. And I would just be looking at the list of numbers. So this would be 1 plus a fourth, sorry, not plus 1, a fourth, a ninth, a 16th, and so on like that. And I would just be asking, is this list going anywhere? And yeah, it's going to 0. And we did that a long time ago, and it's not too bad. You just take the limit. And you say, oh yeah, that's 0 because there's only n's on the bottom. So the bottom grows and makes it be a fraction, and so you get 0. But the series is a completely different beast. We're adding up the numbers. And so many more tricky things can happen. So when you want to think about this, we actually have to do a lot more work. We need to find the partial sums and deal with those. So we need to think about, okay, what's S1? S1 is just adding up the one term, 1. S2 is adding up the first two terms, 1 plus a fourth. S3 is adding up the first three terms, 1 plus a fourth plus a ninth. And we need to see if this is going somewhere. So they're two different things. This list, we have to figure out if this is going anywhere. And what's tricky is this is what SK would be like. So you just add up until you get to K, the kth term. So the trick is that you need to find some sort of nice formula for this, but that's often very hard. We did it for the other one with the 1 over 2 to the n in the previous example. This one's much harder actually to do. But then once you have the nice formula, you would do this limit. And then whatever that is the limit. And that would tell you if it's a number, then it would be converge. Otherwise, if it's not a number, like it goes to infinity or it just diverges, then that would tell you that the series diverges. The original series being this thing. So there's a lot more work to do. And it's very hard. It's very hard to find a nice formula for this guy that you can take the limit of. You cannot take the limit of it right now as it looks, because you don't have an explicit formula for it. You just have it as it is. Okay. So next time we'll do lots of examples, right? And this time there's only really one real example. But next time we'll do more examples. Okay, see you then.